Let us understand the concept of central limit theorem using this example. Let us consider a random variable x and let it be represent the outcomes of rolling a dice. There are 6 possible outcomes: 1, 2, 3, 4, 5 and 6. Each of these have the associated probability of occurrence. So outcome of 1 is possible among the 6 possible outcomes. So the probability is 1 divided by 6. We represent it as fraction. And we can put it here for all the 6 outcomes. The expected value of the outcome x, or what is the value we expect to see on the face of the dice, which is given by xpx. So we will simply find the sum product of x with p of x. So the expected value is 3.5. We can similarly calculate the standard deviation of x. In this case, since the probability is same, we can simply use these values to calculate the standard deviation. So this will be standard deviation. We'll consider this as a population. And we compute it. That turns out to be 1/5/7. Let's represent this as a number. So that is 1.7108. Let's kind of keep it until 4 significant digits. Now we know these are the outcomes of the dice, and let us say from this population we would like to draw a sample and find the average of the outcomes of the sample to make an estimate about the population outcome. So let us consider a case of single dice roll and determine what is the probability of what is the expected value of the face value of the dice and the associated standard deviation. And we can also make a table of n, e of x and st of x. Let us do this experiment for 3 sample sizes. So let us say our x is 1, 2, 3, 4, 5, 6. Associated p of x is 1/6. Expected value of this single sample is xpx, which is given by some product, and the standard deviation of x is one 1.7078. Let us extend this example to the two sample case. Let's say n1 and 2, and the random variable be the average value of these two outcomes, and we'll find the associated p of x as well. So we'll compute it in a separate table. So the possible outcomes are, we can take a little shortcut to get it. And let's sort this first. Column so that all possible combinations are computed. So if the first roll generates a value of 1, the second can generate a value of 1, 2, 3, 4, 5, 6. Similarly, if the first one generates a value of 2, the other dice could be 1, 2, 3, 4, 5, 6. So you've kind of enumerated and considered all possible outcomes of rolling of two dice. The expected value of one experiment of rolling the two dice is the average of the outcomes of each of them, and that becomes your expected outcome. So when it is 1 followed by 2, the expected outcome is 1.5, and this way we have generated the average value of the outcome for all the 36 possibilities. Now let us calculate the expected value of this by identifying what are the unique values we have and what is the probability of each of those occurrences. So let's remove all the duplicates first. Okay, since it's a formula, I need to paste it as values. And then remove the duplicates. So there are 11 different possibilities. We will calculate the expected value of these possibilities. So in how many ways do we expect 1 to occur? We know the total number of occurrences possible is 36. So we can simply do the count is equal to count if in this range, how many times 1 occur. So 1 occurs once, converted into probability by dividing by 36. And let's copy this formula underneath and see what are the possibilities or the probabilities of these occurrences. Now we can compute the expected value of this using our formula, sum product. Comma okay, I need to put a comma here. So that turns out to be 3.5, and the standard deviation of x is 1.207615. Let's conduct this experiment for a sample size of 3. X p of x let's copy this a few more times. There are 216 possibilities. And let's sort this. Right. So for 1 on the first dice, there are 36 possibilities on the dice 2 and 3. That's what we have enumerated here, and so on and so forth. So we get total of 216 possibilities. Now the random variable is the expected value of this, which will be average we extract the value of x here, paste it as values, and remove the duplicates. So we are left with 17 values between 1 and 6, and let's do the countif. And the criteria is whether it is 1 or not. And we see the occurrences for each of these. Let us divide by 216 to arrive at the probability. And let us calculate the expected value of x. And the standard deviation of x. Sum product. And standard deviation is we calculate it, and we see as the sample size goes on increasing, the standard deviation goes on decreasing, but the expected value continues to remain same. And let's kind of fill this table with 1, expected value 3.5, with sample size of 2, expected value is again 3.5, and the standard deviation is this. When we go to the sample size, here so we see that as the sample size increases, the standard error keeps on decreasing. But there is a very interesting relationship this shares with the population standard deviation, so which can be calculated using the formula sigma divided by square root of n. So we will just point it to root powered with 0.5, and we don't want this reference to change. This is empirically calculated standard deviation, and this is the standard error we are calculating using sigma by root n. And we see that in any which ways we calculate it, the values are exactly same. Let me also do the visualization of this. Sample of n is equal to 1. We don't need the legend. Let's kind of shrink it to a similarly. Let's again take this to a plot, like this, and is equal to 2. Similarly, let's calculate it for the sample size of 3. This is too crunched up, so let's eliminate this so that we are able to see all 3 of them laid one over the other. Similarly, let's do it for the sample size of 3. We know this is n is equal to 3. So what we observe is, as we increase the sample size, the expected value continues to remain same, but the standard deviation of the sampling distribution decreases So central limit theorem is, irrespective of what kind of distribution the population has, the sampling distribution will always tend to be normal, will always be normal for a sample size of 30 and above. The expected value of the sample and the expected value of the population will be same, but the standard deviation of the sampling distribution, that is your standard error, will be or can be calculated using the population standard deviation divided by root of n. That's what is the central limit theorem.